So good day to everyone. So in this video, we will discuss about orthogonality and diagonalization. So without further ado, let us go to our first example. So suppose we have the matrix A with entries 3, 0, 0, 0, 5, 1, and 0, 4, 2. So I will be giving the values of the eigenvalues right away and their corresponding eigenvectors. So I'll be assuming that um, the viewer will already have the skill of computing for the eigenvalues as well as their corresponding eigenvectors. So lambda 1, the first eigenvalue will be equal to 1, and a corresponding eigenvector will be the vector 0, minus 1, 4. Lambda 2 will be equal to 3, from which we get the eigenvector 1, 0, 0. And then lambda 3 will be equal to 6, from which we get uh, the vector v3 with entries 0, 1, 1. Now, first of all, we can try to check about the orthogonality of every pair of eigenvectors that we have determined. Orthogonality simply means, in basic language, perpendicularity. So we can check whether V1 is perpendicular to V2. In this case, it will be perpendicular, or the two vectors will be perpendicular because the dot product of V1 and V2 is equal to 0. Similarly, V2 and V3 will also be orthogonal or perpendicular because, again, their dot product is equal to 0. However, if you will check the status between V1 and V3, then you will find out that this is not equal to 0. And so this tells us that the set of eigenvectors of A is not orthogonal. So again, it is not orthogonal because we have found a pair of eigenvectors in the set of eigenvectors in which those two eigenvectors are not orthogonal or not perpendicular. All right, so from here, we try to form a matrix M where the columns are actually the eigenvectors of the matrix A um, in the order that they are presented here in our example. So in particular, our first column for M will be 0, minus 1, 4. The second column will be 1, 0, 0. And the third will be 0, 1, 1. And if you will try to do the calculation for its inverse, you will be able to find out that its inverse will be given by the 3 by 3 matrix with entries 0, minus 1/5, 1/5. So that's for the first row. Second row will be 1, 0, 0. And the third row will be 0, 4/5, and 1/5. What's interesting about this is that if you try to form the product of matrices M inverse times the original matrix A times M, then what we will get is exactly a diagonal matrix where the entries of the main diagonal are exactly the eigenvalues of A presented in our original order of eigenvalues. So the entries of the main diagonal of D will be 1, 3, 6, and everything else will be equal to 0. And so from here, we're able to show that the matrix A is equivalent to a diagonal matrix where the elements of the main diagonal are exactly the eigenvalues of the matrix A. So we now go on to another example, and this time around we want to be able to give an example where the eigenvectors of A are actually orthogonal. So let's try to consider another matrix. So for our second example, let us try to have the matrix A where the entries are as follows. We have 17, minus 2, minus 2, and then minus 2, 6, 4, and minus 2, 4, 6. And just as in the first example, I will again present the eigenvalues with their corresponding eigenvectors to be able to get ahead and go to our outcomes and result the quickest possible way. So lambda 1 will be equal to 18, and v1, its corresponding eigenvector, is minus 4, 1, 1. We also have lambda 2, which is 9, and v2 can be 1, 2, and 2. And then lambda 3 will be equal to 2, and v3 can be 0, minus 1, and 1. Now, if you try to check the status of orthogonality or perpendicularity between any two pairs of these eigenvectors, so we will have v1 dot v2 will be equal to v2 dot v3 will be equal to v1 dot v3, and a common value will be equal to 0. So this implies that the set of eigenvectors of A is orthogonal. One good thing about orthogonality of the eigenvectors is the way we will be able to form the matrix inverse of the matrix M. So how do we actually form the matrix M if the eigenvectors are orthogonal? So first consider N1, which is just V1 divided by its magnitude. And in this case, it will be equal to minus 14 over square root of 18, 1 over square root of 18, and 1 over square root of 18. Note that the magnitude of vector v1 is actually square root of 18. Also, define n2 to be v2 divided by its magnitude. And in this form, n2 will be equal to 1/3, 2/3, and 2/3. Again, I will allow the viewer to be able to verify later that the magnitude of v2 is just equal to 3. Finally, we form the vector n3, where the entries are 0, minus 1 over square root of 2, and 1 over square root of 2. And this is under the knowledge that the magnitude of n3, or v3 rather, is equal to square root of 2, and n3 is formed by dividing v3 by its own magnitude. And so with that, we can now go on and form our matrix M. So matrix M will now be equal to minus 4 over square root of 18, 1 over square root of 18, 1 over square root of 18. The second column will be 1/3, 2/3, 2/3. And the third column will be 0 minus 1 over square root of 2, 1 over square root of 2. Now, one advantage of dealing with an orthogonal set of eigenvectors is the fact that if you try to form its inverse, then all you have to do is to consider its transpose. So in this case, what we will get for its inverse will be minus 4 over square root of 18, 1/3, 0, and then 1 over square root of 18, 2/3, and minus 1 over square root of 2. And for the last column, we have 1 over square root of 18, 2/3, and 1 over square root of 2. So this is basically the advantage of using an orthogonal set of eigenvectors. That is, we are saved from further computational complexity of evaluating the inverse of the matrix M. And so now, from here, we can say that if we multiply M inverse with A and then with M, then this is just the same as the transpose of M times A times M, and this will yield a diagonal matrix where again the elements of the main diagonal will be the eigenvalues of the matrix A presented in the order where it was originally given. So it's going to be 18, 9, and 2 for the elements of the main diagonal, and everywhere else will be equal to 0. So with this in mind, one good question that can be asked is, how do we actually tell or see whether for a given matrix we will get a set of eigenvectors that is orthogonal? Well, one sufficient condition to be able to obtain a set of orthogonal vectors or eigenvectors is the fact that A is symmetric. So if A is symmetric, that is, if A is equal to its transpose, okay, then this will imply that the set of eigenvectors will be orthogonal. And so as a consequence, the matrix M that will be formed is such that M inverse will actually be equal to its transpose. And so that's it for our discussion. Thank you very much for listening, and I'll see you in the next video.